redox reactions, aka oxidation-reduction reactions, are a very, very important reaction. Not just for this class, but also a lot of majors in general. Like, I love redox reactions. I was a biochem major, and so redox reactions was my bread and butter. And so it's great. It's literally everywhere. Literally, I can go on and on. Anyway, so what even is a redox reaction? Well, first, let me define the word species. So you're going to often see the term species being used, and it's just another word for a component or a compound, just like something in a reaction. So if you're talking about a substance, species is just another word for it. And species is used a lot for redox, so just as an FYI. Okay. So you do not need to know this, but you might run into it, so I'm going to tell you now. You have these two terms, reducing agent and oxidizing agent. The College Board test, you do not need to know this, but if you look up other resources to learn about redox, you might see it. You don't need to know it, so just as an FYI. Okay, so let's continue talking about redox. So, oxidized is when a substance loses an electron. And so reduced is the opposite. That substance is gaining an electron. And so there's mnemonic to memorize this. I love mnemonics. I love weird ways of memorizing things. And so you could memorize Leo says grr. And so lose electron is oxidation. Gain electron is reduction. So easy way of memorizing it. It's a very common mnemonic. I will say I did not make this one up compared to other mnemonics we've learned in class. But it's a great one. It's perfect. It's great. In order to identify redox reactions, we need something called oxidation numbers. And so it's a weird definition. So imagine you have an atom, and if it had a charge, what charge would it be? Assuming they were kind of like ionic things. And if you're like, what the heck is that? It'll be easier with an example. So just to reiterate, oxidation number again helps decide redox stuff. So you'll see if an element is oxidizing, you'll see if an element is reducing in a reaction, and it's only if any of them are. So you might not necessarily have a redox reaction because you have to check, okay? And so in order to identify it in a reaction, unfortunately, you need to memorize this. I have the link to the rules on the class website. It's under Unit 4. I also am going to go over it here. So first, in a reaction, if I straight up have an element by itself, again, it has to be by itself, the oxidation number is going to be 0. So for example, if I have a reaction where it's iron plus something makes some other stuff, well, that iron is by itself, so therefore it has an oxidation number of 0. That includes the diatomics because they're technically by themselves. So if I have Cl2 or O2 in a reaction, that automatically is going to be an oxidation number of 0. Okay. So if it is a monatomic ion, so mono being one, atom being, well, atom, ion, it's whatever the charge normally is in an ionic compound. So, for example, NaF, Na is a monoatomic, so Na is positive 1, so therefore it's going to have a plus 1 for its oxidation number. The F minus is monoatomic, so that is going to be minus 1. Now with the other example, the Na3PO4, well, Na is still monatomic, so that's still going to be plus 1. but the PO4 is polyatomic ion. So you have to treat the P and the O separate, and we'll talk about something like that later. Okay, hydrogen specifically has its own thing, okay? So we assume it's +1 if it is with a nonmetal, because it's kind of acting ionic in a way, right? So for example, HF, so hydrofluoric acid. We have the H and the F. So the H is going to be +1, the F is going to be -1 for this oxidation number. If I have H2P, H is going to be +1 each. So you have two H's, so it's a total of +2. But again, each H is +1 for oxidation number. So the usual things you see, it's acting like an ionic thing. Now, if it's reacted to a metal, then that H is going to be a -1. So you see the sodium and the H, well, that H is going to be -1. And the sodium is going to be +1, okay? So keep that in mind. So metal versus nonmetal on who it's reacting with. Okay. Oxygen, almost always -2. There are barely any exceptions. You don't need to know all exceptions, but you do need to know in general there can be. It's just almost always it's going to be -2. So one exception actually is going to be something like hydrogen peroxide, H2O2. So the H is +1 and the O has to be -1 because again the formula is H2O2. And you need to make sure that the oxidation numbers add up to 0, similarly to ionic stuff. Anyway, you have the neutral compounds, which is what I was alluding to in the example that I said. Anyway, they have to add up to 0. So like what the hydrogen peroxide one, H2O2, the H had to be +1 and the O had to be -1 because each of them are +1 each and -1 each respectively, and so we had to be neutral. Okay, so polyatomic, the charge equals the sum of everything. So if you take a chlorate ion, so chlorate again is one of the ones you had to memorize. And if you forgot it, give me a second. Okay, so if you forgot it, that's going to be ClO3 -1. Okay, and so because it is ClO3 -1, the charge for the oxidation numbers has to equal -1. Okay, and so since I know oxygen specifically is -2 usually, then I'm going to treat that as such. So ClO3 -1. So since each oxygen is -2, 3 times -2 is going to be -6. And so I need to think about what needs to be chlorine. There's only one chlorine, so X -6 is -1, and so therefore X has to be 5. And so the oxidation number for chlorine is going to be +5, and then the oxygens are going to be -2 each. Okay, cool. Fluorine is always -1. I don't know why it has its own special rule. In comparison to the other elements, just make sure to know that too. So again, unfortunately, you have to memorize this, but hey, it's not too bad because most of it is just following ionic stuff. So, not too shabby, not too shabby. Okay, so we're gonna go over some examples because I'm sure some of you are confused with the rules. Why do we need to know them? How do we even use them? So we'll talk about it. Yep. So we have xenon tetrafluoride. So xenon is going to just be Xe. Tetra is the prefix 4. Fluoride is fluorine. So there we go. So first you just straight up need the formula. Next we're going to follow the rules. So this is a neutral compound. So the total needs to equal 0. So again, total equals 0 when you add all these up. So we need to look at the rules to see what these things are. So fluorine is always -1. So I'm going to put like a little -1 down here. There are 4 of them in total, so we have a total of -4. And xenon, assuming it is similar to ionic stuff, that would be +4 because 4 minus 4 is 0. So again, each fluorine is -1. So the oxidation number for fluorine is -1. I did this math down here purely to know what the xenon's oxidation number is. So be very clear on that because that's a very common mistake students make. So again, fluorine is -1 each. I put -4 here because there's a total of 4 of them to do the math to find out xenon being +4. So again, be very, very careful. Okay. So next one, potassium dichromate. So this is an ionic compound with a monoatomic and a polyatomic. So we have K2Cr2O7. Okay. It is a compound, so the total has to equal 0. So again, remember that. And so I can do this based off the rules. So first we have the monatomic ion of K. So each K has to be +1. And so I have 2 of them, so the total is +2. Okay. Then the oxygen is usually -2. So I'm just going to go ahead and put -2 here. And so 7 times -2, that's going to be -14. So we have 2 chromiums over here. So thinking about algebra, if you want to write it as an algebra equation, well, we have 2 plus 2x minus 14 is 0. So that x has to be, what do you think? 6? Yes. Because 6 times 2 is 12, plus 2 is 14, 14 minus 14 is 0. So each chromium has to be +6, because this needed to be +12 over here. I did the math in my head, but I mean, you could do the math long if you'd like. So that's how you would show the oxidation numbers for these guys. So for the last example, we do the regular thing. So calcium hydroxide, that's going to be an ionic compound. So you just do the normal stuff for writing that formula. So Ca parentheses OH parentheses 2. And so Ca is a monoatomic ion. So that's just going to be +2 because that's the normal charge in ionic. Then we have our hydrogen is +1 each. There's 2 of them because there's the parentheses, so that's going to be a total of +2. And then oxygen is the one we're trying to figure out. There's 2 of them though, so 2 times that. Okay, so we have to add those up because the total is going to be 0. Okay, and so since the total is going to be 0 because it's a compound, we could just do algebra. So we have 2 plus 2x plus 2 equals 0. And so when you math that, x has to be -2. So the oxidation number for oxygen is going to be -2. All right, so here's a problem. We have chlorine, sodium bromide, we got sodium chloride, and bromine. So go ahead and do the balanced equation first, and then I'll talk about how we use oxidation numbers in order to figure out oxidation and reduction in a problem. The Leo says GER part is going to come into play, and also the oxidation numbers I just went over. So go ahead, pause the video, do the balanced equation. Okay, so here's our balanced equation on the left, so you can see it right there. I have the rules on the right again because I'm going to refer to them in order to do oxidation numbers for this whole reaction. So first, let's do the chlorine. So here is chlorine. It is an elemental form by itself, so therefore the oxidation number of this is straight up just 0. I can do the same thing for Br2, so I'm going to go ahead and put that over there. So then I need to do the oxidation numbers of every single element in every single compound. So we have Na and Br. That is a ionic compound, so I could treat it as I do for ionic stuff. It is also monatomic for each of them, so it's straight up just the charge. So sodium is going to be +1, bromine is going to be -1. Same for this one, we have a +1 here, -1 here. I'm not worried about coefficients, I'm just purely looking at the oxidation number of the formula, okay? So the next thing you need to do when determining who is reducing versus who is oxidizing is looking at the oxidation numbers and how they changed for each atom. So, for example, we have the chlorine over here. The chlorine went from 0 to -1. So I'm going to just go ahead and put a note so I know, so I don't have to like look at this back and forth over and over again. And then the other thing that changed is the bromine. So the bromine went from -1 to 0. The Na is +1 to +1, so that didn't do anything. So I'm actually just going to write that down just for reference. So +1 to +1, so nothing happened. We don't need to worry about that guy. Okay, so we need to look at these situations and we need to think, who is gaining or losing electrons based off the charges changing in these oxidation numbers? So we have to be careful, right? Because this is easily flipped. So we went from 0 to -1. We gained an electron because electrons are negative, so this became more negative. So since it went from 0 to -1, it gained an electron, and as a reminder, gaining electrons is reduction, therefore chlorine went through reduction. Because again, gained electron, reduction. And so the bromine went from -1 to 0. It became more positive. It lost an electron. And so losing electrons is oxidation, Leo. And so hence I can label this as oxidation. So that is how we use redox identifying based off the rules you need to memorize. So again, you need to memorize. All right, so here's your turn. So you're practicing exactly what we went over on these last few slides. So write a reaction, determine oxidation numbers, and then decide which one's going through oxidation, which one is going through reduction. So go ahead and pause this video and then try it yourself. Ready for the answer? Let's go. Okay, so we have our balanced equation, which is just listed there. I have nothing to say other than, hey, you should know how to balance your stuff already. Okay, so then we have the oxidation numbers to identify in the second question. So just to reiterate why they were the way they are. So this silver is by itself. It's elemental, so that's 0. The H2 is an elemental thing by itself, so that's 0. We have H2S. H is always +1. If this is a compound, it always has to equal 0. So since we have 2 H's, that's +2 in total. So therefore, the sulfur needs to be -2. You could do the same thing over here. So this is +1 for the silver. There are 2 silvers total. There's a -2 on that sulfur because this is an ionic compound, so we just treat it as an ionic compound to identify oxidation numbers, and so that's why those numbers are the way they are. So we notice the silver is going from 0 to +1. We lost electrons, so it's going through oxidation. We have the H going from +1 to 0, so it's gaining electrons, and it's going through reduction. If you're like, oh gosh, I don't quite get it, I'm confused, well, the next part will help you immensely. At least I think so anyway. Okay, so redox reactions are the full reaction. You can write something called a half reaction, which is showing which part is oxidizing and which part is reducing. Because when you combine those two things, you make a redox reaction. So a half reaction is just separating those two things. So make sure to know that. So if it's asking for a half reaction, it's literally asking for both parts. So showing oxidizing separately, showing reducing separately. And of course, I will show an example of that. Here is a generic example on the screen. So if I'm losing electrons, you start off with whatever you were, and then that electron goes bye-bye. It's going somewhere. So you show the electron separate. There might be more than one. This is just a generic template. You put the blanks of whatever substances there are there. And then gaining electrons, so you start off with a substance. It's going to gain an electron, hence why it's on the reactant side. And then you make whatever it is reducing to. Okay? So we have here steps on how to do it. So first, you just need to write a good old regular balanced equation. Nothing else. You just make sure that you can do that, because that's just what it is. And so then you do, again, the same stuff that I just talked about, which is the oxidation numbers of everybody. And then you got to check, is this even going through redox at all? Because if it's not a redox reaction, then you can't do a half reaction. So you have to check, is it even going through redox at all? Is anything oxidizing or reducing? You got to check. Then, if it is for sure a redox reaction, then you can write your half reactions. And so you want to make sure, this is important, that the charges of your oxidation numbers are conserved. You also want to make sure that your mass is conserved. So if you have this many on this side, this many on this side, they need to be conserved. And some of it is going to go against what we normally do when it comes to reducing down, because students are not used to having to balance electrons, and you'll see what I mean with the example. All right, let's go ahead and go over an example. So here is a reaction situation. So write a good old balanced regular equation. Pause the video, and then I'm going to talk about a couple things. Okay, ready? Here we go. Now, before we even actually go over the balancing part, there's a couple assumptions we can make about states of matter. Now, I'm not saying you need to know this. It would be nice to know this, but you don't have to know this, okay? You can logic it out. Again, we technically have that one solubility rule you needed to memorize that I've mentioned in a previous section, but you could guess some states of matter just by reading the problem. So, first of all, can two solids mix? So it straight up says solid cobalt, and then it happened to say lead 2 chloride. You can't really mix two solids together in order for it to react. Things need to be mixing well enough. Two solids are just touching each other. Nothing is going to be exchanged by doing that necessarily. So it doesn't make sense to have two solids. So the state of matter for the lead 2 chloride would most likely not be solid. So that's just an assumption I can make from the get-go. Now, lead 2 chloride is an ionic compound. However, it has a very high melting point. So it doesn't really make sense that we would have liquid lead 2 chloride. Nor would it make sense I have lead 2 chloride as a gas. So the most likely state of matter it is aqueous. Again, it's not going based off the rule you memorized. This is just going based off logic from other things we've learned about. Okay? And then products, well, it says lead precipitate. So lead is for sure making a solid. It is not easy to make two solid products. So the cobalt 2 chloride probably isn't a solid. And going by the ionic liquids having high MP and BP, it doesn't make sense to be a liquid or a gas, so most likely that's aqueous. And so that's why I have the states of matter that I have on the bottom. Again, did you really need the states of matter for everything? No, but I could make some good assumptions just based off logic. And so that's why I wanted to talk about the logic of how I figured out those states of matter. But again, you don't really need to know that. You just need to know, again, the one rule to memorize. And if they give you the solubility rules, then make sure to apply them if they do give it to you. Okay, so the second thing to do is to write down oxidation numbers. I highlighted these for a reason. You'll see why in a second. So go ahead, pause the video, and identify the oxidation numbers for every single atom, and then I will talk about it in a moment. Okay, ready? Here we go. So we have elements by themselves. So we have the Cu on the left by itself. So that is an oxidation number of 0. We have the Pb on the right. And so that has an oxidation number of 0 because, again, it's an element by itself. The compounds in the middle, those species are ionic. And so we can treat them as ionic. So the lead has to be +2, the chloride has to be -1 each. And then for the cobalt to chloride, same thing. The cobalt's +2, the chloride ion is -1 each. So that's how I got my oxidation numbers. So we do have some changes in charges. So I highlighted it there just so you can see it, because the cobalt went from 0 to +2. The lead went from +2 to 0. So those changed specifically. Therefore, it is a redox reaction. Okay, the third thing is checking if it's a redox. And so we obviously did, because I saw the oxidation numbers change. And so now we can write the half reactions. Again, mass and charge must be conserved. So here's our, again, equation with the oxidation numbers. And so for the half reactions, you need to focus on the ones that are highlighted because they changed oxidation numbers. So here I have the cobalt. And so cobalt went from neutral cobalt to a charged cobalt of +2. And so in order to make sure that charge is conserved, I need 2 electrons on the right. The lead went from +2 to 0. So the electrons have to be on the left side because I'm going to add +2 to 2 electrons that are -1 each. And so that's why it's 2 electrons. And then it became Pb. So those are our half reactions. So make sure you, again, mass is conserved because we have CO and CO on both sides, and then the electrons are conserved. The charge is conserved because we want to make sure if the charge is 0 on one side, the charge has to equal 0 if adding together on the other side. Okay, in this second example, I have eliminated spectators. We're just going to focus on the ions because I want to emphasize something in case you don't have the full reaction with spectators in it. So go ahead and just decipher the above and write it kind of like an equation, a normal balanced equation thingy, and then identify the oxidation number. So go ahead and pause this, and then I'll talk about it in a moment. Ready? Here we go. So here's aluminum. Here's our nickel ion. We're making an aluminum ion. We're making regular nickel. So those are our charges. Great. Everything looks fine so far. However, it is not balanced. You'll see why with the half reactions. So here's our oxidation numbers. Good old ions versus neutral element by itself. Okay. And so first we have the aluminum here. So the aluminum went from 0 to +3, and so there needs to be 3 electrons on the right. On the nickel part, however, you gotta be careful. It's +2 charge to 0, so there's 2 electrons on the left. But things need to be conserved. It doesn't make sense that one thing is changing 3 electrons and one thing is changing 2. That does not make sense. So the electrons are not balanced, so we need to actually balance them. So I'm going to show you how. Okay, so here's our half reaction. Here's our other half reaction. Now, in order to make sure the electrons are the same for both half reactions, I can do some multiplying. I can make both of them have 6 electrons in each half reaction, so that way we're always using 6 electrons for both. And so, for the aluminum one, I can multiply everybody by 2 in order to get 6 electrons. And then for the nickel half reaction, I can take that equation, the half reaction, and multiply it by 3. So I'm going to go ahead and do that. So for the aluminum one, again, I multiplied everyone by 2. So I added a coefficient of 2 on the Al and the ion form. And then I have 6 electrons in total because 3 times 2 is 6. I'm going to do the same thing for the nickel one, where I multiply everybody by 3. And so here is nickel, where everybody is multiplied by 3. So I got 3 of the nickel ion, and then 6 electrons, and then 3 of the nickel that's just good old regular nickel. And so here's the correct balanced equation because of redox. So you take the coefficients that we used in the half reactions in order to balance the charges. So the masses are still conserved because 2Al to 2Al. It's just the electrons were not balanced, and so I had to balance the electrons in order to have the correct balanced redox reaction. So that's the tricky part that might happen. So be very mindful of that. You need to check your electrons are balanced as well as your mass being balanced. Alrighty, here is your turn. So go ahead and pause the video and try it yourself. Okay, ready? Here we go. So, here's our thing. I put a 2 there because you need a 2 there. And so I reiterate checking oxidation numbers and then checking half reactions to make sure it's balanced. So here is my checking of that. So my nickel had 2 electrons. I had to make sure my half reaction for cobalt also had 2 electrons involved. And so you can see my work here. The cobalt is +3 each, and there's a 2 that needs to be in the front of that. So you see this is CO2. So there's 2 cobalts. There's 2 cobalts over here. That's where these 2s are coming from. I forgot to highlight this one. But otherwise, there's 2 electrons. So that's great. Now, if you noticed, you don't always have to equal oxidation number of 0. The cobalt went from +3 to +2. It changed. It just didn't become 0. Again, you don't have to go from 0 to -1, -1 to 0, or whatever. They can be from any number to any number. If the numbers change oxidation number-wise, then it is a redox reaction. So, there we go. There's our good old balanced equation. Now, most of the time, writing a balanced equation is fine. It's just good to double check, if it's a redox reaction, to double check that the electrons are balanced too. So it's already balanced nicely. We're chilling. So what can be asked on the AP test? So if it says the phrase, balance the following redox reaction, that means do the regular balance reaction that you normally do, how we normally have done it. Make sure to find the oxidation numbers. Do the half reactions. Do we need to balance the electrons? And then you could do net ionic at the end. So we have this example right here. So pause the video and do a regular balanced reaction first. So our normal balanced reaction is right here. Now, did you necessarily know aluminum chloride is AQ? No. I use the same logic that I mentioned earlier where I would know it's AQ, but again, you don't have to know that. Hydrochloric acid, you know, is aqueous usually. You don't really have that as a solid. You usually have it as, you know, a solution because it is an acid, so that's why it's AQ. But the aluminum chloride one you didn't need to know. I just, again, logicked that out. But again, you do not have to know that. Okay? So, oh, here, I even mentioned it here. Aluminum chloride, probably aqueous. Again, similar to what we have discussed, logic-wise. So, I'm going to do the oxidation numbers. So, here's the oxidation numbers just to save time. So, there we go. And so, from those oxidation numbers, we notice that the aluminum has changed. It went from 0 to +3. And then the hydrogen change, it went from +1 to 0. So those are our species that happen to change. And so I can go ahead and do the half reactions for those. So here I have my aluminums from the balanced equation, and then I made sure to know which is which, and then the electrons as well. And then I have my hydrogens. I noticed that my electrons indeed cancel out, so that's good. And then the masses are conserved because the amount of aluminums that I have, the amount of hydrogens I have, everything is nice and balanced. And so I could do the net ionic, and so that's literally combining the half reactions. So the left side is the aluminum solid with the hydrogen in aqueous, and then we have the aluminum and then the H2. So that's pretty much how you write net ionics using half reactions if it's a redox problem. So you combined a whole bunch of things at the same time. Yeah, it's not too bad once you practice it enough though. All right, so here's your turn. So try it out yourself, pause the video, and then I'll go over it. All right, here we go. So for that first one, we're just deciphering the above. There you go. So it's just putting the ions. Cool. And then we write the half reactions based off oxidation reduction. Cool. So the iron is +3 and then +2 on the right side. So that means it gained an electron because the charge went smaller. So that's reduction because gain electrons, reduction. And then the tin is Sn, and it has gotten more positive. So it lost electrons, so that's why it's on the right side. I needed to make sure the electrons balanced, which is why the iron has a 2 in the front of everything, because the tin had a +2 electron on the right side, and so I had to make sure I multiplied the iron's half reaction by 2. And so my balanced reaction is the 2 coefficients that are on the different irons that exist. Cool. Okay, so next one, here's our chlorine gas doing its thing, and then you have the balanced equation, and then the net ionic is the stuff that changed. The sodium did not change oxidation numbers because it just was +1 to +1, so that is not it. But the net ionic is just making sure that it is the ions that are changing oxidation numbers. And yep, that's it. It's similar to what we did in a previous section, essentially. So there we go. Okay. And then for this third example, so we have the iron 3 chloride and stuff. And so I have this little note here about the iron probably being in solution, but again, not stuff that super duper matters. Okay. So here's our balanced reaction. And so this is with something, but it didn't matter for this problem, so that's why I didn't say specifically. And so the 2 half reactions, we have the chlorine becoming chloride ions, and so there are 2 of those technically. And then we have the 2Fe to make the Fe plus 3. And so just be mindful, be careful. Okay. Now, if you also notice, the half reactions were reduced down because you can. So if I originally wrote down the 3Cl2 and then I had the 6 chloride ions on the right side for that half reaction, I'd have way more electrons involved. So I reduced it down before writing the net ionic, because again, you just can. And so in this example, I did. So there you go. So how does this even relate to real life, in case you're curious? Well, there's like a bajillion examples. So one is just good old combustion. So the example I have here is just regular hydrocarbon with however much carbons and hydrogens in it, which is why it just has a variable X and Y. And then you are reacting with oxygen to make your two products, and then you have heat involved as well. That's where the delta H is coming in. So, good old fuel stuff. We have so many biochemical reactions that are redox reactions. You got your metabolism in order to make like ATP and all that stuff. You have respiration, good old breathing and then taking it out. So literally every biochem reaction is dang near, if not all of them are redox reactions. I can't confirm that off the top of my head, but to me, from what I remember in my undergrad days, dang near all of them were redox. So that they're literally everywhere. And then batteries. Batteries are going to be super important in Unit 9. And redox is so big in batteries, so big. And then corrosion of stuff, especially with metals, those are generally also redox reactions. There's so many things. Okay? So recap, what did we learn? So we learned oxidation and reduction, the terms. We learned about oxidation numbers so that you can determine whether a reaction is even redox or not. And just, good old things. So just make sure you know your redox stuff and we're good. All right, that's it for this section. Bye.